So you think of the hardware. To realize complex devices like smartphones, we implement SoC, system on a chip. So we use various kinds of processors like CPUs, GPUs, digital signal processors, accelerators, neural engines, security engines. So we make use of various processors to build the engine. And then we also use various kinds of interface IPs. When it comes to on-chip communication, we implement it using bus called AMBA, mostly Advanced Microcontroller Bus Architecture defined by ARM. It's license-free. You can download the specification from ARM website, and then you can think of implementing your own chip. So in this case, this is AMBA. It has various flavors like AXI for high-performance processors, AHB for pipeline communication, and APB for low bandwidth devices. And AMBA supports synchronous parallel communication. So the communication happens almost like synchronous and parallel within the chip. To communicate with the external world, we prefer various kinds of interfaces like high-speed serial communication through USB, or the other interfaces could be like UART, SPI, and I2C. And then there will be different kinds of memories, and there will be other kinds of components like wireless components for Wi-Fi and Bluetooth. And obviously, this kind of chips will have system controllers. System controllers will have all the necessary hardware components like oscillators, PLLs for the clock generation, power management unit, and timers, watchdog timers, all the necessary things. And all these components can be efficiently connected with the external pins through GPIO, general purpose IOs. It could be a simple embedded microcontroller. You can think of using Riscv ISA for complex SoCs, also for simple embedded microcontrollers. So in this case, the CPU will be connected with the interfaces through AXI bus. In case you want to connect some low bandwidth devices like timers, then you can think of using APB. In that case, you may need bridge. So there could be interfaces like UART, GPIO, and there could be bridges like AXI to APB and AXI to AHB. The processor will be using AXI interface. It will be an AXI master, and then it will be connected with various slaves like APB slaves and AHB slaves. Let's look at the compilation process. We use higher level language for the software development, languages like C, C++. So using compiler, we convert the higher level language into assembly language, which is nothing but the processor instructions. And using assembler, we convert the assembly language into machine language. Let's look at how this happens. For example, there is an equation. It's in higher level language. Using Riscv compiler, when we compile this into processor instruction, it is going to produce the assembly language like this. This is how the assembly program is going to be. And shift left logical and I. Then using assembler, we convert the assembly program into machine language. That's where the assembler follows the ISA. So based on the ISA, it's going to convert the instructions into 32 bits binary like this. This is what we are going to discuss as part of the base ISA. Let's look at the compilation process. For example, you have the C code, sum.c. You compile it using Riscv compiler. It will produce the assembly code .s files. And then using assembler, you would be able to generate object codes .o files. There will be other libraries. Then using linker, we can link all the files and produce executable program. And then using loader, we should be able to execute the program. So Riscv ISA provides the interface for both toolchain and processor. The embedded folks use Riscv ISA to create the toolchain. When I say toolchain, it includes compilers and assemblers. So whatever the application program created by the software programmers, application developers, they compile the application into machine language using compilers and assemblers. So embedded systems engineers, they create the tool chain, and the software programmers use the tool chain to convert their software application into binary machine language. And the chip designers refer to the ISA, instruction set architecture, and they implement the processor. So whatever the binary we generate, the binary will be loaded into RAM, and then eventually the processor is going to execute the instructions in terms of binary. This is how you can visualize the RISC processor reduced instruction set computer. There is a special register called program counter. There are various general purpose registers. It has various components like decoder, arithmetic logic unit, and there are memories like instruction memory and data memory. So you can visualize the execution in 5 stages overall: fetch, decode, execute, memory, and write back. This is what we are going to explore as part of the RTL module. How we can implement any Riscv processor. It could be a 3-stage processor or 5-stage processor. That's what we are going to explore. Using this formula, we calculate the CPU time, which is nothing but seconds per program. So here, the performance can be improved by improving algorithm, or by changing the programming language, or by optimizing the compiler, or by implementing an optimized hardware using ISE. But if you look at all these parameters, like algorithm or programming language or compiler, we would be able to control 2 parameters. One is instruction count, the other one is CPI, clock cycle per instruction. But if you want to improve the clock frequency, the only possible way is implementing the optimized hardware using ISA. That's what we are going to explore in the RTL module. Let's look at the difference between high-level language and assembly language. We use higher-level languages like C, C++, Java, System Verilog. But when we say assembly, there will be assembly language for Riscv, ARM, x86. As part of the higher-level language, complex data structures like struct, class, and array. But when it comes to assembly, the execution happens in terms of bits, bytes, words, and integers. And we can think of implementing complex controls using if-else, nested if-else, for loop, while loop. But in the case of assembly, we can implement everything using control transfer instructions, branch and jump instructions. Higher level languages use arithmetic and logical operations. Here also, arithmetic and logical instructions support all arithmetic and logic operations. Higher level language, they are suitable for application software, implementing mobile apps, UVM test bench. And assembly language reflects the ISE. So whatever the software we implement using higher level language, basically we convert them into assembly language using compilers. And further, we convert the assembly language into machine language using assemblers. That's the main difference between high level language and assembly language. Thank you.